So I'm from Washington University, and this work was supported in part by a grant from a few years ago with Jeff Williamson. These are the collaborators. I want to give special thanks to Bruce Whiting and to a graduate student, Norbert Ibeko, who both helped me with the presentation. Jeff Williamson from VCU and Josh Evans are both here, and Jeff is a longtime collaborator. And I want to point out that some of the methods that I'm going to talk about here have been implemented successfully in a chemical engineering application where there are two gamma ray sources with different energies, and they're proving very useful in some chemical engineering reaction column analysis. So I'm going to start off with talking about data models and reconstruction algorithms, and then I'll move on to talking about the image reconstruction approaches. And I think all three of the speakers before me highlighted methods where they first computed images and then processed those images later. And one of the things that I'll try to talk about is what are alternative approaches. And all three of those approaches really rely on those two images being very good to start with before you do that subsequent processing. I'll then talk about a simulation study using a particular alternative approach, which is a dual energy alternating minimization algorithm where all the data are processed jointly to form two images at once. I'll talk a little bit about how to quantify performance, and then we'll conclude. So I don't really think we need much more motivation. We've had a lot of motivation in this session and a session yesterday. And so these systems are available today. We need image reconstruction algorithms now. And I would argue that we want to think about deriving algorithms that are fundamental in that they're based upon an understanding of the underlying physics, and they can be easily transferred from one of these systems to another and be able to compare across these systems. I'm going to come back to this slide in a little bit, but just to give you an idea of the way that I think about all of the algorithms that I've seen. They can be thought of as you take your sinogram data, you do some processing on them individually, there's some joint processing, and then possibly some post-processing afterwards. And the question is, in which one of these boxes or which ones of these boxes do you put your imaging, in which do you put your taking linear combinations, et cetera. So let's go back to basics in part to try to set the notation. We're going to use S of E to model the source spectrum with energy E. And so that would be, say this curve here, which would be after whatever filter there is in the path. So Beer's law, in terms of the attenuation mu, would give us a spectrum that looks something like this, which is the spectrum leaving the body. It will be incident on the detector, and of course we have the beam hardening shift of the mean energy. I'll use I naught to denote the total mean number of photons per detector. So this S of E is normalized to integrate to 1. There's a detector sensitivity spectrum, which I'll denote by D of E, and so phi of E in my notation will be this source spectrum times this detector sensitivity spectrum. So this the mean number of photons incident on a particular detector is given by this formula here, I naught times phi of E times e to the minus the line integral through the attenuation function. And then the total signal at a detector with it just being the integral of that overall energies up to the kVp. Typically, when people think about doing image reconstruction, they refer to a linear image reconstruction or filtered back projection. And just to review that, you would take your data. So your data would be given up here in the numerator. That's the approximation we got in that last slide. So that would be our model for the data over here, the sinogram data. You normalize it relative to an air scan. You do your beam hardening correction, and that's correcting to a target energy. The target energy I refer to here as E bar. Take the negative log of that, and that's approximately, the argument is that that's approximately the line integral at that target energy. You do filter back projection on that to get your estimate of the attenuation function at that energy. And then you may display that, or you may display something else just to be consistent with what I show later in the dual energy. I'll normalize that here relative to water, the attenuation of water at that energy, and so then this C that I'll display here and later will be unitless. So what's the problem with that? Well, one problem has to do with what are detectors? What is it that they do? So the detector sensitivity includes the probability that a photon of energy E is detected. Given that a photon of energy is detected, if it's a photon counting device, then the response is just going to be 1 for every photon and accumulates the number of photons. If it's an energy integrating detector, then for every photon that's incident, the response is going to be that energy, and then there could be some other response. As far as detector statistics, if it's a photon counting detector and you view Beer's law as the survival probability, then the Poisson distribution is the right model for the data. If it's an energy integrating detector or some other response, then a compound Poisson process model is the right model. If it's a Poisson distribution, then just to remind you, the log likelihood function is just going to be the data times the log of the mean minus the mean, and that's just obtained by taking the log of the Poisson distribution and keeping the terms that depend upon the mean. So we're left with a couple different possible approaches to forming images. One is a deterministic model, which is kind of like what the filter back projection argument is. You'd say you have a deterministic function, the data equal a function of the desired image, and you want to invert that function to try to recover your image. You may have some measure of error, and you try to find the attenuation function that's closest to the data in some sense. On the other hand, if you have a statistical model, then you have the log likelihood function, and the typical approach is to use that log likelihood function for inference. Usually we look at maximum likelihood image estimation, possibly penalized, and so we want to find the maximum overall possible attenuation functions of the log likelihood function. So continuing in that vein, if we index source detector pairs by Y and voxels by X, we'll assume that the data are Poisson distributed. This J here will indicate which one of the scans it is. So if it's dual energy, J is either 1 or 2. If it's multiple energies, J would be 1, 2, 3, however many you have. The means will be G of G sub J will be the means. And so the log likelihood function is just the data log of the mean minus the mean, and then the model for the mean will discretize those integrals, so it'll be a sum over energies, and then this H is just the point spread function corresponding to the line integral through the attenuation function. There's a beta here which can account for mean, background, or scatter. I'm not going to focus on how we deal with scatter today. The mean unattenuated counts, I sub j, could be different for the two energies, 2 kVps, and so over here we show the standard spectra for the 140 kVp and the 80 kVp. So the attenuation function will model as being a linear combination of basis attenuations, mu sub I. So just talking a little bit more about the attenuation function approximation. There are a couple of approximations. There's the usual one we always use when we form images and we think about pixels or voxels, which is function approximation in the spatial domain. But then as far as energy, we'll think of it as being a linear combination of these basis functions. There are various ways we can think about the basis functions. So let's just talk down here. The standard is from Alvarez and Minkowski, which is separated into the photoelectric or Compton scatter. But as we've seen in the earlier talks, there are other ways of doing it. You could be fat and bone, or fat and tissue was mentioned earlier. You could use a signal processing approach where you just take all the spectra you have and do a singular value decomposition and keep the top two. Or you can hand select them. So, for example, calcium chloride solution and styrene, which is one that we use in some of our work with Jeff Williamson. You can also have a constrained system, and Rainer Raupak used this when he had that triangle up there in his slide. That triangle was really just saying that you have three components and you have a non-negative linear combination between those three those three corner points, and the sum of the contributions of each one is equal to 1. So you have this third equation that gives you 3 equations and 3 unknowns, and so you can solve it in that case. If we take a statistical approach, then we're led to an iterative reconstruction algorithm, and there are various approaches for that. I'm going to focus on the approach that our group takes, which is an alternating minimization algorithm. Josh Evans talked about this algorithm earlier today. And so there's several papers from our group, including a TMI in 2007. The algorithm is guaranteed to monotonically increase the log likelihood function. This is just that mean data that I had on the previous slide. And so to avoid having to write this whole thing out, everything inside of that sum I'm just going to denote by Q. So this G is just a sum over the energies of this Q. And the goal is to maximize the log likelihood function over these images C. And the method is shown schematically in the bottom right. The data come in, we compare the data to the mean predicted data, we use that to update the image, and then take that image, go put it back through the forward model, or that's actually the pair of images through the forward model, and then we do the comparison. The way we do the comparison is somewhat unique. We compare the back projection of the predicted mean data to the back projection of the data. This is the data, not the log data. Okay, and so that's a unique way of doing it, and that's the way we get a guaranteed monotonic increase in log likelihood, and it's based upon convex optimization. And so there's more about that in our paper. So let me go through the image reconstruction approaches quickly. So this is the setting in which all of them will live. So we have multiple sinograms. There is a somatome definition CT scanner at the Mallinckrodt Institute of Radiology and the Center for Clinical Imaging Research, and so we sometimes think about modeling that because we have one. And I guess I found out yesterday that there's also a Philips dual energy system on our campus. Anyway, you take those two or from any of the three previous talks would give us our two sinograms which go in. We've heard about the technologies earlier. Let me just go down to this last point under the selected issues in image use. In our work with Jeff Williamson, he's interested in doing radiation therapy planning, and he's often interested in reconstructing an image in the sort of 20 keV to 40 keV range. So using these images to look sort of at this lower energy range for radiation therapy planning. So we'll be thinking about that as we go forward. So there are different ways of assigning where the image is. You can do the imaging afterwards. That is, you could do your normalization beforehand, take a logarithm, take some combination. Here I've said linear, and then reconstruct the images. Or you could do a nonlinear inversion here. This is discussed in a few places, including by Callender et al. In 1988, where these G functions are just the means we had earlier, where in the L's are the effective lengths of any given line. You put them into these this post-processing image reconstruction. Alternatively, you can use the methods that we heard earlier, and I have linear combinations here, but this could be a nonlinear processing where you reconstruct images individually and then combine them in some way to get your two component images. Or you can put in here the statistical image reconstruction algorithm. And in fact, if this iterative reconstruction algorithm is the one that I said earlier, then you're not going to need any of these other four boxes. So let me go through quickly through a simulation study of this dual energy algorithm. And so I only have a couple minutes to go through this, so I'm going to go through it rather fast. Our first simulation had a large phantom where this is 20 centimeters across here. This is a lucite shell. There's water between the outer lucite shell and an inner lucite core. The inner lucite core has 4 holes drilled into it that can be filled with various substances. And these are two component images. And so for the standard, what I'll call the basis vector method following Jeff Williamson et al., there was a calibration scan where you took measurements of this exact phantom with these holes filled in with the whatever you choose. And then there was a second scan, which is a test phantom, where there was muscle, equivalent ethanol, Teflon, and some fictitious substance X, sort of a heavy bone-like material placed into this upper left, the 10 o'clock location. And then from the calibration phantom, you got your components that you used to reconstruct the individual components, and then from the test, you applied that linear mapping. as opposed to the AM dual energy algorithm, which I talked about on the last slide, which has no pre-correction of the data, does not use the calibration data in any way, and also in what I'm showing here, we don't have regularization. This just shows the fractions of the materials used. The substance X is a heavy bone-like material. Many of the others have a higher styrene concentration. So here's an example of the two, if these are the two truth images, these are reconstructed using filtered back projection in this basis vector method. This is the calcium chloride component, this is the styrene component, and you can see that there's significant artifacts down here in this calcium chloride component. But if you'd use those to synthesize images, so for example, you synthesize an image at 65 keV, which is close to the mean of the 140 kVp, both of these perform rather well. But if you're looking down at that lower energy where radiation therapy planning says you might be interested, this image has less noise, and we'll quantify that in a minute. One way to quantify it would be through cuts through there where we see the filtered back projection here in red. It's a lot noisier than this AM dual energy at the 20 keV image, 65 keV. They're both about the same. We then did a smaller phantom where we only had 360 source positions, 92 detectors. It's a 60 millimeter phantom, so it's really just the inner core of that other phantom. And we use only 64 by 64 images for a reason that hopefully will become apparent in a little bit. So there's a styrene component and the calcium chloride component, and again, we see that the dual energy does a little better. The filtered back projection has some streaking artifacts between these two components. The synthesized images, again, the 65 keV looks pretty good on both. I'd say this one's a little bit sharper. There's no regularization, again, on either of these. The profiles, there's, again, the AM dual energy is better. Let me skip that and say that one of the things that we're interested in doing is looking quantitatively at how well we can reconstruct the attenuation in an area. So we looked at an area inside each of these rods, the muscle, ethanol, Teflon, substance X, and then in the lucite near the edge and near the center, and we looked at the relative errors. There's an absolute difference of the estimated attenuation divided by the truth as a function of energy. So it goes from about 20 keV up to 140 keV, and so these are all non-negative, of course, because it's absolute divided by the truth, and these are in percents. And this is only 10,000 counts, and the AM dual energy is significantly lower than significantly better than the filtered back projection. The percent errors are significantly lower. If we multiply the number of counts by 10, the errors here continue to go down. The errors here go down a little bit, but not nearly as much. We multiply the number of counts by 10 again, and we get negligible error here on the AM dual energy, and we still have several percent error over a large range on this on the filtered back projection method. So sometimes we want, we're also looking at how we can quantify performance analytically. And so before we can quantify it analytically, let me just show that these are from 15 realizations with 100,000 counts. These are the mean images. These are the variance images. These variance images are on the same scale. And so we say, well, the variance of the filtered back projection versus the AM dual energy for the styrene component, this variance is much higher. And the mean has some artifacts as well. Calcium chloride component, again, for filtered back projection, you have some artifacts, and the variance is higher. And the question is, can we compute that analytically? And so I would argue that yes, we could using the Kramer-Rao bound. So the question you can try to ask when you look at a Kramer-Rao bound analysis is, if you go to one point on the image, say this point, and you say, well, how does that affect my estimate over here? Or similarly, how does a point in this component, if this is the styrene component, that's the calcium chloride component, how does a point there impact my estimate over there, and does it? So the answer is yes. You can. So what you can do is you can compute the Fisher information. So the Fisher information for this problem is this is 64 by 64 image, and that's 64 by 64 image. You pile it all up into one big long vector, which is 8,192 big. You got to compute the Fisher information, which is 8192 by 8192, and you invert that to get the Kramer-Rao lower bound, which is then a lower bound on the variance of any unbiased estimator. So you get this huge matrices over here. These are calcium chloride from one. This is like these components here, one point to another point for calcium chloride and styrene. They're cross components between a point there and a point there, and so every point on this image corresponds to one of those. You invert it, and then you look at the diagonals, and you get something that looks like this. And you say, well, okay, this substance X is the hardest thing to estimate, and I can look at the variance of these two components relative to the Kramer-Rao lower bound. And then I want to point out here that these are on different scales. So if we put them on the same scale, I'm going to change it. So now they're on the same scale. The relative performance relative to the Kramer-Rao lower bound of the AM dual energy is much better. So the point here is that we can quantify performance, and we can ask. It provides a way of quantifying what performance is achievable independent of the algorithm. That's this left column. And then how well your algorithm approaches what is achievable, those are the right columns. So with that, I'll conclude. So we reviewed some models for reconstruction, outlined the various approaches for dual energy CT image reconstruction, tried to put them all in a common framework. We did a simulation study, and the argument that I would make is that if we take an approach that's based upon the statistics on log likelihood function, that we're going to do better.
I mean, I'm certainly convinced about dual energy CT. As a novice to this, though, I do have a question regarding performance parameters. A number of systems were presented, and some metrics are listed, like, in terms of atomic number, separation, resolving power, and even this Kramer-Rao. But those are all at fixed, in terms of fixed spatial resolutions. Is there going to be any work towards development of something like, DQE, maybe a multidimensional system where you're looking at spatial frequency and resolution? So what work's been done? Because one of the problems I see is how you handle NPS. When you have a dual energy, it's not at all obvious to me how you do that. And I think something like that is needed, because we've got 4 vendors, there are pros and cons, and I can't really tell which is better, but there should be some metric beyond vendor-supplied phantoms.
So I guess a question for the vendors that are here. Typically, when you're in the lab, you're working on things, you have metrics you're trying to optimize. Have you looked at these types of measurements?
I think you can take a step at a time, looking at all the conventional measurement, because eventually you still produce images. So the images can still be measured, quantified, and so forth by spatial resolution, noise power spectrum, all those characteristics. Granted, you have a lot of more complex processing stuff and so forth. But to the radiologists, what they see finally is the image presented. So that's one aspect. The other aspect is more quantitative, because historically with CT, you cannot really have a quantitative measurement in terms of accuracy and so forth. We only guarantee water or soft tissue, but the rest of them is sort of up in the air. So dual energy for the first time gave you some chance where you can actually measure against the phantom, see how accurate your prediction is and your measurement is.
So it sounds like that's an opportunity and need for development.
So this is a non-expert. So are there DQ analogs available that the vendor supplies? So if we want to buy one of these systems, I can look at them? I mean, is there work done on that?
I think they're not published, but they are available in principle, yes.
Okay. Sabe?
I'm wondering whether optimization has been done for dose ratio between low and high, and also in terms of thickness of the filter that you chose, or even material, and as a function of patient thickness, would you consider maybe changing the KVP of the low? Because you chose 80 KVP. Is that optimal?
Well, you're right that the 0.4 millimeter of tin, for example, that we are using is, of course, a compromise. A thicker layer of tin would further improve the spectral separation, but also reduce the available flux in the high-energy spectrum, of course. And to achieve the optimal performance for a specific size, yes, there's also an optimum thickness of the filter, yes. In principle, yes, but practically, of course, it's a problem to implement that into a system.
So how about dose ratio between low and high? Maybe, Dr. Russell, did you consider that for the simulation?
Actually, I didn't do the simulation myself, but I think it was, first of all, the simulation was done to have equal dose for all of them. And I remember that the dose ratio was chosen so that the low KVP has much higher MAS. So for the 80 KVP, I think this was your question, it had at least 3 times the MAS, which is what I believe quite reasonable dose ratio. But I think my colleague from Siemens can certainly be more precise on that because he knows, of course, more details about this system.
Yes, for equal noise, you will even need more than a factor of 3. That's true. That's why we have two different modes, 80 kV and 140 plus tin, and 100 kV plus 140 plus tin. So depending on the object size, you can choose the best combination in terms of dual energy performance and power requirements.
So one of the assumptions when you do dual energy is that the line integral is along the same line between the 2 kV images, correct? So when you do, for example, kV switching, the focal spot actually shifts perhaps in the X-ray tube. And similarly, with the dual source tube, how does one kind of handle that and make sure that the ray paths are actually the same? I mean, that's one of the advantages of having the same tube with the phosphorus detector. So I was wondering if you could comment on that.
Okay, I start. So in dual source CT, we have a calibration of the two systems against each other. So they are calibrated within a few microns to be sure that you know the geometry. Of course, they are not exactly parallel or see exactly the same plane at the same time, but you know the mismatch, and this is corrected during the reconstruction.
You know, for the fast KV switching, if you look at the tube design, there are actually 4 different control nodes available, mainly to try to control the stability of the focal spot, the size, and so forth. So there's actual care taken care of to do that. Another thing is in the details, you know, a lot of times devils in the details. So in the details of the reconstruction algorithm, there's a lot of steps that are utilized, try to overcome, you know, even if there's a residual non-exact overlap and so forth. Unfortunately, I can't talk about what we do.
So there is a price you pay in resolution when you have to do all these corrections, correct? Could you comment on what the magnitude and the change in resolution is from just a single KV image to any of these decomposed images?
Well, I think as the typical limiting resolution today is 0.3 millimeters of a CT system, maybe it's well below, I think, the residual error after correcting.
Yeah. Maybe you meant for the KVP switching of Dr. Xie, right? Right. Okay.
We did the MTF measurements. So based on the MTF measurement for the same kernel, you know, you have to, because there are different reconstruction kernel and so forth. For the same kernel, it's the amount of degradation in your word is negligible. It's definitely below the variability, you know, from system to system.
Thank you.
Okay,
I actually have a clinical application question because one of the applications presented, virtual colonoscopy. In terms of I guess the current thinking, not necessarily exclusively, but majority of people think, virtual colonoscopy based on the conventional CT is inferior to the conventional endoscopy. And I think most people would agree, not necessarily all, but that's the majority thinking. With dual CT, do you see that becoming on par or even exceeding it? Because I think that's the kind of application that perhaps is suited for something like this. Because I'm not quite convinced of all the applications I saw, but something like a virtual endoscopy. I mean, that's if I go out there, should I get this rather than the conventional?
To be honest, I'm not. I cannot say I'm competent enough to answer this question. I really don't know. So that's all I can say there. I know that there is improvements by doing the dual energy with respect to conventional. That is visible, and that is actually was demonstrated in a clinic in Hadassah several times. So this was one case, but there is no, to my knowledge, no clear evidence whether it will be on par or even better than other methods.
Yeah, because I mean, right now, conventional CT is useless because you got so many false positives, false negatives. You might as well just go for the real thing.
There's another big complaint about CT virtual colonoscopy is if you see the polyps, you can't do the biopsy right away. And that, even with dual energy, triple energy, you can't solve that. So that is still going to be.
Question regarding the sandwich detector. You had an optical filter between the two detectors.
X-ray optical. I mean, this.
Is it?
Yeah.
I was wondering, is it possible to make it into a X-ray filter so you increase the separation?
That is what it is. There is a layer in between the two which filters part of the radiation, about 3% if I'm correct.
So in
order to increase the energy separation, because we heard that it's a drawback of this technique that the energy separation is not as good as in the KVP switching techniques. And this is exactly for that reason. Okay. You lose DQE, of course, because some of your X-ray photons are absorbed without giving a signal in the detector, but you gain, nevertheless, in separation and dual energy separation quality.
So you made it as thick as...
Well, it's of course optimized, so to be acceptable, compromise.
The second speaker said that one of the advantages of two-source dual energy CT compared to conventional CT is reduced dose. And as I understood, it is because you remove low energy side from high energy source by using thin filter. I am wondering why it is not possible to achieve in conventional CT.
Well, it is possible if you, so to speak, add up both spectra to an effective spectrum. Like you do in the mixed image. Then it was shown in one of the experiments that it's really equivalent to using a KVP in between. So if you add 140 plus tin filter and the spectrum of 100 kV and mix those two data sets, the resulting image is, well, I have to say almost comparable because you have higher energies than 120 kV, but it's almost comparable to doing a conventional scan with 120. This is the reason why I said it's dose-wise it's equal. So additionally, you get more, of course you get more information than from a conventional scan that you can add as a clinical value, and you completely get rid of, or you might get rid of, a second scan that would have been necessary today without contrast agent. So in this sense, well, you save approximately 50% of dose if you use it that way.
It's getting late. I would like to thank the speakers for coming and talking openly about their technologies. I think it's been very informative. Let's give them a round of applause.